Hello, everyone. Today I'll be talking about the topic for the ACSL third elementary division competition, which is Boolean algebra. So, you may have heard about algebra in school, and algebra is a topic in math that involves the manipulation of numbers. On the other hand, Booleans are a type of data type that only have two values, which is true and false. Therefore, Boolean algebra is the manipulation of expressions involving true and false. So, to begin, let us look at some problems and go over some strategies. So this asks us to evaluate the following expression as either true or false. And this problem is a pretty good representation of the basics of Boolean algebra. So first, we look at the different expressions. We see we have not and or. So there are many different expressions in Boolean algebra. Or sorry, not expressions, operations. And these operators are and, or, and not. So when using and, both of the conditions on either side, they must both be true in order for it to be true. So if this side is true and this side is false, then the output will be false. But if both sides are true, then the output will be true. Or on the other hand, only needs one side to be true. So unless both are false, then it will be true. Not, on the other hand, will take the opposite of something. For example, not true equals false and not false equals true. It just reverses it from true to false or false to true. Also, just like in algebra, we can also use addition and multiplication to represent and or, where or is addition and is multiplication. So if you see these, it just means and or or. On the other hand, you might also see not represented by a tilde, and that just means not. Okay, now let's look at this problem on the left. So let's look at the stuff in the parentheses first. We have 3 plus 5 is less than 7. So this is 8 is less than 7. And we know that this is false. So we can write that into our expression. So now we have not false, or in this expression we have 4 divided by 2 is greater than or equal to 2, which is 2 greater than or equal to 2. That's true. And 7 times 3 greater than 25, which is 21 greater than 25, which is false. And here, we know that not false is reversing false, so it will be true. And then true and false, for and, both of the sides have to be true in order for it to be true. But here we have one false, therefore this is false. Now we have true or false. Because we're using the operator or, this only requires one side to be true for the entire thing to be true. Therefore, the answer is true. Okay, let us look at a different problem now. How many ordered pairs will make the following statement false? So here we see that the problem is asking how many ordered pairs. And if we see this wording, we generally know that we must use a truth table. A truth table involves simplifying the given expression as much as possible and then making a table that will compute the values at the end. For example, if you have the expression a and b, where a and b are variables, then you can create the following truth table. A, B, A, and B, where these two columns represent the two possible inputs and the column on the right represents the output. So here you can simply plug in the values that are possible for A and B. And here we see that in Boolean algebra we commonly use 1 and 0 to represent true and false respectively. And we can see that this makes sense because A and B is A times B, right? So anything times 0 will become 0. So this perfectly fits in with the definition of the operation and. So we can fill in this table easily, like this. Again, 0 represents false, and 1 represents true. Okay, now look at the problem on the right. First, let us simplify this as much as possible. So we have not A or B, and B, and not A. So we see that there are two ands in this expression. So that means in order for this statement to be false, then only or one or more of these components must be false. So here we can create a truth table, and that's method 1. And I will shortly explain a different method. Now let us create the truth table as follows using the different components. Oops, wrong color. Since there's only two variables A and B, this will be pretty simple and there will only be 4 possible cases. So here, let's fill out the third column first, not A or B. So here A or B is 0, so not of that is this. A or B, so these are all zeros, like this. Not A is 1, 0, 1, 0. So in order for the final result to be true, then these 3 columns must all be true. And we see that this never happens. Therefore, the number of correct answers is 4. We can also use a second method to solve this problem. So note that in order for the expression to be false, then only one of these actually needs to be false. So it's easy to see when B would be false, which is when B equals 0. And it's easy to see when A would be false, which is when A equals 1. And then, so for not A or B to be false, then A or B would be true, which means that A is 1 or B is 1. And if A is 1, you could also have B is 1, or you could have B is 0. And if for B is 1, you can have A is 1 or A is 0. And you can actually see just by doing it out that all 4 scenarios are possible, so the answer is 4. However, generally, method 2 isn't recommended because it's not reliable, and having a truth table makes it so that the casework is clear and that you're less likely to make mistakes. Alright, let's look at another problem. Determine which ordered pairs make the following statement true. So here we see that it uses the symbols to represent this expression, but if we wrote it out in words, it'd be not A and not B, or A and B. And you kind of see that order of operations will make it like this, where multiplication takes precedence over addition and the tilde takes precedence over multiplication. Let me write that down. So not is first, then and last or, and this will go from left to right. Okay, now we can create a truth table. We can create a separate column for each part, which will make it easier to evaluate. Again, there are only these 4 possible cases for A and B. Not A is 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0. And then the final result would be not A plus not B. Sorry, not A times not B plus A times B. Which here you can see this is 1. This is 0. This is 0. And this is 1. So it's asking which ordered pairs will make the expression true. And you see that here, the expressions are true. So the ordered pairs are 0, 0, and 1, 1. Alright, let's move on to our next problem. Simplify the following Boolean expression using the fewest operations. So this is a simplification problem. And it's asking how to simplify not of A or B or not of A or not B. Now we must use some of the rules of simplification from used in Boolean algebra. So in general, there are 10 rules of simplification. First are some of the ones that you might be familiar with if you learned some algebra skills. One is the commutative property, which tells us that A times B is equal to B times A, where times means and A or B is equal to B or A. This is pretty self-explanatory. We also have the associative property, and this says that A or B or C is equal to A or B or C, and A and B and C is equal to A and B and C. Furthermore, we have the distributive property. And this tells us that A and B plus C, A and B or C is equal to A and B or A and C. So these first few rules are pretty self-explanatory. But next we have De Morgan's law, which is important to pay attention to because this is one that you'll probably use frequently. So I'll put a star around it. De Morgan's law tells us that not A or B is equal to not A and not B. In essence, you can distribute the not, but you must change the inner expression from or to and. And there is a second application of De Morgan's law, which is equally important and very similar to the first application, which tells us that not A and B is equal to not A plus or not B. So again, this is very similar. So you can see that De Morgan's law basically allows you to expand the not, but you must change the operation. After this, we have a few more trivial properties. For example, A or 0 is equal to A. A and 0 is equal to 0. A or 1 is equal to 1. And A and 1 is equal to A. If you don't understand these yet, then think about them a bit and figure out why they work. because this will help you better understand Boolean algebra. Next, we have A or not A is equal to 1, because 1 of A or not A must be 1. And then A and not A equal to 0, because 1 of the two must be 0. Next, we have A or A is equal to A, and A and A is also equal to A. Finally, our 10th rule, if you apply not twice, not of A is equal to A. Great, now with these simplification rules in mind, let's go back to the previous problem. Which asks us to simplify this Boolean expression. So here we can see that we can apply De Morgan's law. So this becomes not A and not B. We have this. And here, again, since we have a not on the outside, we can apply De Morgan's law again to be not A. And then now we must change the or to an and. And we have not of B, and we know that this is simply B. Now we must see how we can simplify this expression further. So now we can factor out not A from these two parts. And we can see that we can factor this because we can write or as we can write or as plus. And actually I made a mistake here because we should be writing it with the same form every time. Because here in the problem it writes it with the symbol arithmetic operator, so I should keep that when I simplify it. So now we have something like this. And then we can reverse the distributive property. So this would be not B plus B. And we know that not B plus B, one of the two must be 1. So this final will end up to be 1. Then the answer will just end up to be not A, or to keep it in the format of the problem. Okay, so throughout this problem, I made a small mistake, which was that I didn't keep the same formatting as the problem. So in general, for simplification problems, you should use the form with the operators, like use this form, because it's easier to see simplification opportunities, such as factor. And in general, you should use a consistent form throughout the entire problem. So instead of using not, I should have used the tilde, but it worked out in the end. Okay, finally, let's go on to our last problem. which asks us to simplify a Boolean expression so that there are no more and operations. And remember, and is represented by the multiplication symbol. So first we see that we have some areas where we can simplify. So first we factor not A, and we factor not B. And we know that B or 1 and A or 1 are both equal to 1. So this would simplify to not A or not B. And as you can see, we have already gotten rid of um all the and operators. So the key of this problem was the factorization, and that is something to look out for in as you are doing problems.